you can see that the first term doesn't depend on theta, right? It's just theta I. That goes away. The second term, you can see, is a linear dependence on theta. So the second term will become gradient j theta, theta equal to theta I. And then the last term is a quadratic dependence on theta, right? So you have minus 2 alpha theta minus theta I equal to 0, right? We just took the Lagrangian. We have a constraint optimization. We took the Lagrangian. We took the gradient with respect to theta, and we set it to 0. Okay, so now we'll do a little bit of algebra here. So you take this over to the other side. You can say that the gradient is equal to 2 alpha theta minus theta I. Right, so what do? We took this objective, we formulated the Lagrangian parameter alpha, we took the gradient, we equate it to 0. Right? And so the gradient is going to ignore the first term, doesn't depend on theta. The second term is a linear dependence on theta. The third term has a quadratic dependence on theta. So overall, this is going to give us like this objective, which I'm going to rewrite over here, be a little cleaner, is equal to 2 alpha theta minus theta I, right? And so now you can move over the 2 alpha to this side and say 1 over 2 alpha times the gradient plus theta I is equal to theta, right? You just like divide both sides by 2 alpha and then move the theta I over to the other side. But this exactly looks like gradient descent now, right? Because you say you've shown that this thing is true, which is saying that theta is equal to theta I plus 1 over 2 alpha times the gradient. Right? This thing you can call your step size, right? But the point is, what we've done is we said, take the Lagrangian, take the gradient, set it to 0, right? Multiply and divide by 2 alpha, and then move the theta I over to the other side. But what that results in is theta is equal to theta I plus some step size, call it epsilon. Epsilon is 1 over 2 alpha. But some step size times the gradient. That's exactly gradient descent. So I guess all I'm trying to show is that you can derive gradient descent by maximizing this objective. Yeah. So it's not an arbitrary objective. Okay, everyone with me? Okay. So we are let me just recap. We took this objective, we wrote the Lagrangian, we took the gradient, set it to 0, did some algebraic manipulation, and the optimal theta for this optimization problem is theta I plus some step size times the gradient, right? Which is exactly gradient descent. Okay, but the important thing is that we're doing this like the steepest descent on a linear approximation under the Euclidean metric. So why might this fail? Like when is this potentially bad? Like doing steepest descent on a linear approximation under the Euclidean metric. So intuitively, we took this approximation and we restricted the parameters to be between a ball. And then we said we're going to do steepest descent. When might that not work?
Or you have all the problems that you would with normal gradient descent in supervised.
What are those problems?
Your step size is too high,
Mhm.
then you might overshoot.
That's right.
Your options.
Perfect. Yeah. Perfect. Yeah. So it only really is only guaranteed for convergence under a particular step size schedule. And so what might happen, as Rico was just saying, is you step too far. And then you like find something that should actually be lower, but you can find something that actually decreases your objective if you step too far. Will they have a similar point? Okay. Right. So that's the first issue that you might have. What's another issue that might happen?
You can get stuck in local maxima.
Local maxima, yeah, absolutely. I think that's kind of a problem universal to all gradient descent, but that's not a problem we're going to be able to fix yet.
Is
I guess it's an issue with supervised learning. I'm not sure if it applies here, but there might be a possible issue where it's like the parameters in different dimensions and different scales, and as a result, you're not actually doing it in an optimal way.
Yeah, exactly. So it's really sensitive to the policy parameterization, which means that if some parameters are like much larger scale than others, they dominate the updates, right? So the reason is the following, right? If you look at the Euclidean metric, Euclidean metric, let's say for a multi-dimensional vector, is weighting every dimension equally, right? And so like some things might be much bigger scales than others. And those like totally dominate your Euclidean norm, right? And so when you have parameters of different scales, the Euclidean ball is going to weight them equally, even though they really shouldn't be weighted equally. Like, or certain parameters might affect the policy more, but they might be smaller scale. A Euclidean metric is not going to account for that, right? So the point is that a Euclidean metric says every distance in every dimension is exactly the same. It's uniform. But parameters, like in a neural net, are all of different scales. They have different importance on the actual policy's behavior. And the Euclidean metric doesn't account for that, right? So what you can see is that gradient descent often looks something like that. And if you like reparameterize your problem, you can actually make it look something like this, even though it's like just a change of variable, right? And the reason is that when you change the variable, the meaning of the Euclidean norm changes. Right? So the key point being the Euclidean norm weights everything the same, and that really is sensitive to the parameterization of your policy. Yeah. Okay. And so this struggles for a deep neural network where you can't control the parameters like very carefully. Okay, so those are two issues. Do these make sense? The first is that because you're taking a linear approximation, right? The linear approximation is only valid for a certain amount I mean, it's approximation, right? So if you step too far, you can do something that actually decreases your value. And so gradient descent only works for smallish step sizes. And the second is that you're sensitive to your policy parameterization because of this Euclidean norm. Yeah, everyone with me? Questions? Like I find this like illustration to be helpful in that like the geometry of your space might be such that, let's say the parameters are along the X and Y dimension. One dimension is way more stretched than the other. Then it holds more importance in the Euclidean norm than the other direction, right? Whereas if you like reparameterize your problem so that every dimension is weighted somewhat equally, then you have pretty different behavior. So whenever you see these kinds of plots, they're like a contour plot. So they're like level sets of your function at different values. And you can have think of gradient descent as taking perpendicular steps to your level set. Okay. Everyone following? These are two additional issues on top of variance. And so we found some ways to deal with variance. We talked about baselines. We talked about causality or like ignoring things in the past. But because policy gradient is doing steepest descent on a linear approximation with the Euclidean norm, you have two additional issues. One, which is because of your linear approximation, and two, which is because of your Euclidean.
Can you give an example of what it would mean to make a more efficient conversation?
Yeah, I'll do it. On this slide. Oh no. Okay, I think for some reason I don't have it on my slides. You know what? I'm gonna pull up something else. Give me a second. I have like a nice intuitive example that I think can help. Yeah. Okay. So for instance, let's consider like a really simple function. Right? So let's consider a two-parameter function, right? So if you have two parameters, theta 1 and theta 2, the gradient of this thing with respect to theta 1 and theta 2 is going to be 1 and 1, right? So it's going to be a vector of 1 and 1. But let's say you reparameterize your function, okay? So we said we're going to have two different things, phi 1 and phi 2. Let's say phi 1 is theta 1 squared and phi 2 is theta 2 inverse, right? It's just a change of variable. So if you change the parameters, and you stick them into your function again, right? the same function, like the same function with this change of variables is now phi one square root of phi one, right? Which is square root of theta one squared plus pi two inverse. So it's theta two inverse. So what we're saying is that this objective and this objective are the same, right? We just did a change of variable. So if you stick, for instance, this thing back in here and this thing back in here, you will still get theta one plus theta two. Yeah. But we just changed our variables to be phi one and phi two, and our objective becomes the square root of phi one plus 1 over phi two. Okay. Just a change of variables. Okay, so we change our variables, and now we compute what the gradient is, and then the gradient looks like this is going to be the gradient of square root of a function, which is 1 over 2 square root of phi 1, right? 1 over 2 square root of phi 1, or sorry, 1 over 2 square root of phi 1, and take the gradient with respect to the second parameter, and it's going to be minus phi 2 squared. Yeah, so just take the gradient of this thing with respect to phi 1 and with respect to phi 2. Right? And now what you do is you substitute in the change of variables back in, and you'll see that the gradients are different, even for essentially the same problem. All we did was change a variable, and really you want the gradient to be the same, right? And so essentially, like what I'm trying to show here is that you take the same simple problem, you change the parameterization, and the gradients look different, right? Which means that it's like really sensitive to the choice of parameterization. This doesn't directly answer your question. I'll get to your question soon. Okay, does that make sense? Like the point I'm trying to get to is that the choice of parameterization affects the gradient. Okay, so let's go back to my current slides. Sorry. Okay. Okay. So Thomas asked a question, how do I change this? How do I change this thing to be more like this, right? What is an example of a good parameterization that makes your gradient better conditioned, right? And so one way to think about this is that we're going to, instead of doing this under a Euclidean norm, we're going to do it under some G norm. And where our G norm is going to change the geometry of the problem, right? So what this is going to say is that normally the Euclidean norm is theta minus theta I transpose G theta minus or theta I, where G is identity, right? So you can kind of think of your Euclidean norm as something like this, and your G norm is often written as something like this, which is essentially theta minus theta I multiplied by some G. And an easy way to think about it is if you have like your theta dimensions, you have some G matrix in your theta dimensions or your theta minus theta I dimensions. Like, and let's say this was like a diagonal, like it like weights different dimensions by a different amount. And so you can kind of think of a G as changing the geometry of your problem because it's like reweighting different dimensions by different amounts, right? So you can, like an intuitive way of thinking about it is, this was your original space, theta minus theta I, you're multiplying it by a G value. The G value is kind of like a matrix, right? It doesn't have to be diagonal, but it's a matrix which changes the geometry. So it like can weight certain dimensions more, can weight certain dimensions less. And so it like helps you go from something that looks like this up on the top to something that looks more like this on the bottom. Right? Now, that still doesn't answer Thomas's question of what G should be. But the first step we're going to say is like, if we chose G as our metric, then how does our gradient descent objective change? Right? So the point we're going to make is that we can change, we did steepest descent, right? So we said, hey, gradient descent is steepest descent under the Euclidean metric. Now we're going to say, let's not do steepest descent under the Euclidean metric, let's do it under some other metric. Yeah. So So the first thing we're going to figure out is if we chose some metric G, where G is just a matrix, right? It's a positive semi-definite matrix. Then what is our gradient update going to look like? What is our steepest descent update going to look like? Okay, so we're going to work out what that looks like. Does anyone have any guesses? Yeah.
Singular value.
It's connected to singular values, but it's going to be like simpler than that. So we're going to follow exactly the same thing we did last time, right? We're going to write out the Lagrangian. So we're going to say theta minus theta I, theta is equal to theta I, minus alpha times theta minus theta transpose G times theta minus theta I, right? And we're going to take this is our Lagrangian. We're going to take the gradient of this thing with respect to theta. We're going to set it to 0. Same thing we did last time, right? We formulated the Lagrangian. The only difference is now there's like a little G sitting there. Yeah.
Just, is it the inverse of the Hessian?
Yeah, exactly. Or inverse of G.
Okay.
Yeah. So Mohammed jumped a few steps ahead of us, but we'll get there in a sec, right? So what Mohammed said is it's going to be the inverse of the G, which preconditions your gradient. But essentially what we're going to do is exactly the same thing. This thing goes away. This thing becomes just the gradient. This thing now is a G-weighted product, right? So one thing I'd recommend is anyone who's doing matrix math, there's a thing called Matrix Cookbook. It's excellent. I just cheat off it all the time. It's great. So if you ever are confused about matrix identities, Matrix Cookbook is great. Or ChatGPT, but either of them. So you're gonna have 2 alpha G times theta minus theta I is equal to 0. Yeah. And so basically your quadratic is weighted by G, which means that your gradient is also going to be weighted by G. You're going to do the same type of algebraic manipulation. You're going to take over this thing to the other side. You're going to say this is 2 alpha G theta minus theta I. You're going to multiply and divide by G inverse. Right? So you're going to say this is going to become 1 over 2 alpha G inverse of the gradient is equal to theta minus theta I, which means that theta is going to be theta I plus some epsilon, which is going to be our step size, times G inverse times the gradient. Okay, so all we did is we worked the same Lagrangian math. We just substituted G norm instead of an identity norm. The Euclidean norm is the identity norm. We just said we're going to have a G norm, right? And so the G norm, it passes our sanity check because it's just going to precondition our gradient by a G inverse. So it's like, it's the Euclidean norm when G is equal to identity. And you can see that when G is equal to identity, identity inverse is identity, which means that it gives you back gradient descent, right? So passes our basic sanity check. But the important thing is that when G is not identity, that's when it's interesting. Like what it allows you to do is it says things that are high in G get weighted low, and things that are low in G get weighted high. Right? And so it's just like preconditioning your gradient. So it's taking your gradient and kind of multiplying it by a matrix, which changes the direction. Right? Just like kind of like rotating. And so going back to the graphical example, like it's taking that gradient and it's rotating it, depending on the choice of G. We still haven't defined what the choice of G is going to be. But all we're saying is that for some choice of G, what's going to happen is that we're going to get an update, which is going to be theta is equal to theta I plus epsilon G inverse times the gradient. Right? So it's gradient descent preconditioned by some G. Does this remind you of any other methods that you've seen in optimization world? It looks like Newton's method, right? So Newton's method is a second order optimization method, which means that you're not just using the first derivative of your update, you're using the second derivative of your update. And so when G is equal to the Hessian, right, which means that you're going to take your second derivative of your gradient, right? That's when this objective becomes the Newton's method. We're not going to do the Hessian here, but it looks a lot like, so what we're going to do is something that is similar to that, but not quite the Hessian, right? So What Mohammed is talking about is like there's a family of faster optimization methods called the Newton's method, where you don't just use the gradient, you also use the inverse Hessian to precondition your gradient. Right? What we're going to do is something we call a quasi-Newton method. Right? And so what we're going to say is that let's try and go back to the intuitive interpretation. Right? So the intuitive interpretation says we want to do steepest descent, but under by like restricting how far the parameters move. So we're going to say we don't want the parameters to move beyond some value. Right? That's what the Euclidean norm says. But who cares how much the parameters move? The parameters mean nothing to me then. What I really care about is how much does the policy change. As if my policy is behaving one way, I really don't want the function to change that much. I don't really care about the parameters changing. I really care about the function changing. And so, 15 minutes later to get to Thomas's question, what do we care about? Well, we care about the policy not changing a lot, right? So this was kind of doing it in terms of the parameters not changing a lot, but we don't really care about the parameters. We care about the functionality, right? The parameter is just a way of like parameterizing a function, and you care about the function, right? So if your function is a policy, which it is here, then you really care about the policy not changing a lot, right? And if we're thinking about a policy, it's probability distribution. So what you care about is the probability distribution not changing a lot. And so we talked about F divergences and KL divergences and stuff, right? So we're saying we want to do the steepest descent, but not under some arbitrary parameter distance. We want to do it under a functional distance. So we want to say that the probability distribution of the policy does not change a lot, right? So that's it. That's the key idea. And so we're going to go from something that has the Euclidean metric, which is that with the G equal to identity, to something which has a G-weighted metric, but we didn't know how to set G. And then we realized we actually don't care about the parameters. We really care about the function. Right? So we're going to instead do steepest descent, but constrain how much the function changes rather than how much the parameters change. Does that make sense? Now you could use a different divergence here. The KL divergence is just easy. Okay, so we said we're sensitive to policy parameterization. We want to deal with it. We're going to try and weight it by some G norm. We didn't know how to set the G norm. Instead, we're just going to do steepest descent with a functional distance rather than a parameter distance, right? So to answer Thomas's question, the thing you're going to use to like choose your G is the thing that affects the policy parameter, thing that affects the action distribution, the probability distribution, not just the parameters, right? Because that affects functionality. And so intuitively, you can kind of think of it as like, you don't want your behavior to change that much. If your action distribution doesn't change that much, your behavior doesn't change that much. So you take little steps on behavior. Yeah. Okay. Yes.
So you're saying that to do this, you were during training, you performing class and then.
I'll simplify it.
Okay.
Yeah, we haven't done that. But in this is we haven't solved this objective yet.
Oh,
This is just the objective we're going to solve.
But they're like, why do I not want to change to a probably better policy?
You do want to change to a better policy, but you're in this linear approximation, right? So you can't just keep going along the line because it's not a linear function. So you have to like constrain your update within some distance where your linear approximation is valid, right? And like what distance do you constrain along? You're saying that theta is going to be better than theta I, but it's just like a bounded amount different because it's an approximation. Yeah. So you're saying that, hey, we started with we're going to do a linear approximation, so it's only valid in some distance, so you can't take a huge step, right? So it's just what distance do you constrain? And it's functional. Yeah. So this is an idea called natural gradient, which is basically saying that when you're doing gradient descent, normal gradient descent is going to be under the Euclidean norm, which is all in parameters, and natural gradient is going to be under this like functional norm, which is saying don't let the function change that much, right? Or don't let the probability distribution change that much. Okay. Everyone kind of with me? Okay, so functional distance, not parameter distance. Okay, so to answer Sid's question, how do we actually solve this, right? We're not going to do some very, very complicated thing. What you can show is that it's kind of hard to optimize the KL divergence, but if you take the second order Taylor approximation of the KL divergence, I'm not going to work it out because it's just kind of a pain to write. But I can link, Jacob, can you make a note for me to link the KL divergence derivation? So you can show that this objective, if you take the constraint, right, you can write a second order Taylor approximation of the KL divergence, and that gives you basically something that looks like this. So the second order Taylor approximation looks something like this, where F is equal to this thing, which is something you call the Fisher information metric. Okay. And so, like, I'm gonna state this without proof, but basically the second order Taylor approximation of the KL divergence is theta minus theta I transpose times this matrix F times theta minus theta I. And F is essentially the outer product of grad log pi's. Right? And so it's kind of like a covariance matrix, if you will, on grad log pi's. Right? So it's telling you which direction is grad log pi sensitive to. So it's telling you, like, in some ways you can kind of think of it as like for which changes in parameters does the function change a lot, and for which changes in parameters does the function not change a lot. So it's like kind of like a sensitivity matrix. Right? Intuitively, you can kind of think of it as like a sensitivity matrix. But essentially what we've done is we've said go from the Euclidean metric to a functional metric, the KL divergence. The second order Taylor approximation of the KL divergence is theta minus theta I. Transpose times F, theta minus theta I, where F is this Fisher information metric on top, which is the covariance matrix, or the average outer product of grad log pi times grad log pi transpose. Yeah. And so you can kind of think of this as your sensitivity. It's like how sensitive is pi theta to changes in the parameters. Right? And so the reason you weight by the inverse of this thing is because you want to make it equally, you want to weight things by how sensitive they are to the policy changing, not by like their scales, right? So to Thomas's question, what F or what G do we choose from the last slide? Well, you take the KL divergence, you take the second order Taylor approximation, gives you this Fisher information metric, and then you take inverse Fisher information. Or you set G equal to your Fisher information. Yeah.
Why is F not equivalent to the I?
Oh, sorry. Good question. This is F theta, and we're going to like evaluate this as theta equal to theta I. Right. So yeah, good catch. That's all going to be theta I. So F does depend on theta I. So you have to. So one thing that makes this tricky, right? So one thing let's try and understand this more carefully, right? So in policy gradient, we computed this gradient. Let's say your parameters were k-dimensional. This is an RK matrix or RK vector, right? Now your F is going to be an outer product of gradients, which means it's going to be a k by k matrix. Yeah. So you have a k-dimensional thing. So this is k by 1. This is 1 by k, which means that your matrix is k by k. Right? So you can kind of think of it on the x-axis are how sensitive is log pi to different parameters. On the y-axis is how sensitive is log pi to parameters, and you have a k by k matrix, which is parameter dimensional by parameter dimensional. Right? And so the tricky part here is that you are now inverting a k by k matrix. And if k is llama, then it's 400 billion parameters that you're inverting. So that's what makes it hard to use. Right? But it is better. Even for, and this is not just restricted to RL, it's also for supervised learning. You can do natural gradient for supervised learning too. But the key points I want to make are, we went from the Euclidean metric to a functional distance. The second order Taylor approximation of the functional distance is the quadratic with the Fisher information metric, which is essentially a sensitivity matrix, right? And then when you like go through the math, it's basically you precondition your gradient by F inverse, right? So you're like trying to normalize the sensitivity across different parameters.
One thing here is since you're doing second order equation, it's just so that it doesn't require the second, that doesn't require the hashing.
Yeah, so it's not actually a second order approximation. It's like a quasi second order approximation. I actually have that on my next slide, but basically it's what you call this a Gauss-Newton approximation to the Hessian. So you can show that your Hessian, I'm going to skip through most of this, but your Hessian is equal to your Fisher information matrix and some second order term. And so what you're going to do in a Gauss-Newton approximation is you're going to like throw this term in here. And so it's like it's a quasi-Newton method. It's a quasi second order method. It's not quite a second order. But the easiest way to think of, there's lots of different ways people think about this. I find the easiest way to go from Euclidean to functional to second order Taylor approximation. Second order Taylor approximation is just inverse sensitivity matrix. And so you precondition your gradient by the inverse sensitivity matrix. Does that make sense? Questions? Yeah. It does. I always get this wrong. I think you want to do it under pi theta because your samples that you're going to take in the new, like theta I was your old parameters and theta are your new parameters. And you want to take samples under your new parameters, not your old parameters.
Theta are my new parameters.
Theta are my new parameters because you're doing math with respect to theta. Right? So it's like theta I was old and I'm searching around old for new. Yeah. Okay. This is a bunch of stuff. Questions, thoughts, concerns. Yeah.
Might be just my lack of understanding of that. But how are the parameters at theta and theta I related to pi of theta and pi of theta? I thought you converted the formula on the top to the formula on the bottom, but somehow like but somehow I like the optimization. Somehow theta actually.
So like I guess it's like when you take the second order, like so this is these are functions whose parameters are theta, right? So which means that it's like a function pi of a given s and the parameters are theta, right? So it's kind of like pi theta is just the function is pi and what changes that function is theta, right? And so the way I got from like pi thetas to actually thetas is when you take the second order approximation, then you like when you do the Taylor approximation of something, you take it's like the Taylor approximation of some f of theta around some theta naught, right, is going to be f of theta naught plus grad f theta at theta naught times theta minus theta naught plus theta minus theta naught times the Hessian times theta minus theta naught, right? And so the reason I got the thetas there is because I essentially took the Taylor approximation of that objective in terms with respect to like some theta I. Right? So it's like when you take the Taylor approximation of a function, sorry, this space is a bit constrained. Let me see if I can just pull up a notability. So if I have like, oh, I guess you guys can't see it. One sec. Where'd it go? Okay, so if I have a function f theta or some function f theta, right? Which in this case is our KL divergence between theta and theta I, right? I can say that this function, if I take the second order Taylor approximation, it's going to be f theta I plus the gradient of f theta times theta minus theta I plus half times theta minus theta I times the second derivative, let's call it the Hessian of f times theta minus theta I. That's what the second derivative is, right? And so I'm going to take this thing as my function, which depends on theta. And I'm going to take the second order Taylor approximation of it. And that's what's going to give me like the theta minus theta i's. Does that make sense?
Yeah.
I think it's because I stated this without proof, it's a little hard to follow because I like didn't tell you what it really is. Let me send you, I found like a nice explanation of it. I'll share it with you and that'll make life easy. Yeah.
Is the reason why we took the second order approximation of the KL all because we're trying to like mimic the Newton method and get
Yeah.
inverse bias?
Right. Or like basically we need to like be able to solve this in closed form. And if it's like a KL divergence, it's like hard to get a closed form solution. So we approximate the KL divergence with its second order approximation, so we can get a closed form solution that looks like this. Okay. Okay, does everyone kind of follow me? We started with gradient descent, good. It had these two problems, large step sizes and sensitive to the policy parameterization. And then we said, okay, we're going to precondition with G. We didn't know what the G was going to be. We made the G different functional distance. We made it from Euclidean to functional distance. We took the second order Taylor approximation and we got this preconditioned gradient, right? And so the nice part about this now is that it's like, what do you call it? You often call it being covariant to parameterization, which means that you can like change the parameterization and it like will not change the gradient. And the point here is that because let's say you change the parameterization, the gradient would change, but the F would also change. And so the F is going to compensate for the change in the gradient. Right? And so the nice part about the natural gradient is that it like it's not as sensitive to parameterization. The other way of thinking about the natural gradient that I find intuitive is that it's saying that you're trying to like, if you're thinking about an RL update, you like start with a policy, you want to like do little steps, but you don't want the policy to change that much. So it's just kind of saying do RL, but constrain how much the policy moves. Right? And then the way we're going to constrain it is we're going to do a second order approximation and precondition the gradient. Or second order Taylor approximation. Okay, everyone with me? Yep.
For like settings where you don't have a policy to change much, if you're doing some type of like online RL.
Yeah.
Sometimes you may want to change very quick.
So it's not that you don't want the policy to change much, it's that you're solving this like non-convex objective shape data. And then you're like taking a linear approximation to it. So in some sense, your linear approximation is only valid in some range. And so you can't, no matter what you do, you can't step that much, right? So it's saying that like, if you take too big of a step, so let's say you're doing online RL, you take too big of a step, then you start collecting really bad data and you start having like tanking performance. So when like folks were trying to do RL, they were just trying to jack up the step size. And then what happens is you're good and you start collecting bad data and you're bad forever. And so instead what they're saying is that you have to take little steps anyways, because it's an approximation. Just do little steps on a functional distance. So you do this for online RL. It's just that it prevents this catastrophic, like, I don't know if forgetting is the word, like getting into catastrophically bad loops of collecting bad data. Okay. So that's the first part of what we're going to talk about. We can skip through this, but you can kind of show that the Fisher information matrix is a Gauss-Newton approximation to the Hessian. So the Hessian is a full second order method, which means the second derivative of your function. If you notice the Fisher information, it does not need the second information. It's just the outer product of the first of the gradients. They're never taking the second derivative. They're only taking an outer product of first derivatives. Okay, so Jan Peters did this in 08 for RL, and they got stuff to play baseball and do things with like ping pong and cool stuff like that. It's so old I couldn't find a video online, but it's really cool stuff. You should read a bunch of Jan Peters' work. It's amazing. Cool. So that is natural policy grids. All we did is we went from a Euclidean distance to a functional distance, and then that led to this like Fisher information conditioned parameter update. Okay, everyone with me, more or less. I think this is one of those lectures you have to go back and look through the slides a little more. But as long as the vibes are communicated, we're good. Okay, questions? Okay, let's keep going. Ooh. So we talked about natural policy gradient. Natural policy gradient is nice, but as we just said, you have to invert the Fisher information metric, which is a K by K or a D by D matrix, right? So even for a conv net, these in the millions, right? And for a bigger model, it's in the billions, right? And so your fish information metric, inverting it can often be really, really painful. And we haven't really talked about our step size issue. So we said if you step too big, you're gonna you might get worse. And so we have to like find a way to pick the right step size. And so the other issue that we're talking about is that the whole thing is still on policy, right? So you look at this update for your policy gradient, every time you need to solve this objective, like the Fisher information metric is also computed under your current policy. Your gradient is also computed under your current policy, right? So whenever you need to take a natural gradient step, you have to take data under your current policy. So we talked about, okay, there's a variance issue. There was these issues with step size and policy parameterization. We solved these, but we're still inherently on policy, right? And so when I think about what's wrong with natural policy gradient, one of them is that you have a huge matrix inversion. Two is that we haven't really figured out what step size will ensure monotonic improvement so that we keep getting better. And we haven't really figured out how to use any past data, right? So we haven't figured out how to use data which is not just on policy. Okay. So this still makes it kind of impractical. So if I'm going to use this with any neural net for images or language which is big enough, like this is not going to work. And so in practice, people don't use the natural policy gradient that much. And so there was an algorithm that John Schulman proposed back in 2015 called trust region policy optimization, which I think is a really cool algorithm, but it's a bit complicated. So we're going to go through that, and then we're going to like simplify it to PPO, which is what people use. Yeah. But the idea behind trust region policy optimization was to say, let's start from natural policy gradient, right? So let's start from natural policy gradient, which is this objective. And let's deal with these issues of inverting the F matrix being hard, step size, and the fact that we cannot use any prior data. We're going to try, the point of trust region policy optimization is to deal with these three issues. Yeah. So the three issues being big F, step size, and like old data. So like, I don't really want to have to keep recollecting data every time. I want to at least be able to take a few steps before I recollect data. Okay, that makes sense? So we have these three issues. We want to solve these three issues, and that's what John came up with this TRPO algorithm. Okay, so we're going to go through these three key ideas one by one. The first key idea is to go from a fully on policy algorithm to an algorithm that is slightly off policy, which means it can use small amounts of data from the past. We're going to use a technique called importance sampling. The second idea is we're going to go from something that is a huge matrix inversion using NP.W or something like that, to something that uses an iterative optimization algorithm called conjugate gradient, which is going to be way more efficient. And lastly, we're going to consider this problem of step size setting, and we're going to use something called backtracking line search in order to set your step size. So there's three big ideas in TRPO. You can think of TRPO as natural policy gradient. So we start with policy gradient. The big pick from policy gradient to natural policy gradient is just saying you want to constrain the functional distance. To go from natural policy gradient to TRPO, we're just going to make three changes. We're going to go from on policy updates to important sampled updates. We're going to avoid matrix inversion by doing this iterative optimization, and we're going to do backtracking line search to set the step size. And so that's going to let us do cool shit like this. And so if you look at like a lot of the updates before 2015, they weren't able to solve high dimensional systems like this. And if you make these three changes with a little bit of John Schulman magic, then you get cool results like that.
So can you help me relate some of this to, I might be not remembering properly, but AdaGrad, where you're adaptively changing how much you're scaling each dimension of your gradient? How does some of this stuff relate to something like that?
That's a great question. I'm not fully remembering the details of AdaGrad, but I guess it's there's like a running average of different parameters kind of,
Yeah,
and
it's basically looking at, well, someone else could probably state it better, but yeah, it's basically actively rescaling the different dimensions of your gradient to.
Yeah.
Same issues.
yeah, I think it's very related. Maybe the very related. I guess there's different rescaling methods. One of the rescaling method in natural gradient is the inverse of the outer product of the gradients, which is kind of like the covariance of the gradients. So I guess one thing I can think of is that it's a full covariance matrix, which means that you can consider how policy parameters depend on each other. Whereas I know that often in AdaGrad, Adam type methods, you consider them independently. And that might be one reason for approximation. Let me do a more informed comparison, because I don't remember what AdaGrad does exactly.
That'd be handy, because I think a lot of us, we learned
Yeah.
Adam and Adagrad.
Yeah.
It's like, that's what PyTorch has through that.
Absolutely. I mean, Adam and AdaGrad is much better than SGD in most cases.
Right.
But how it's interesting to think about how it connects to natural gradient. Hey, Jacob, could you make a note for us to answer that? Okay, I'll post something about it. Thanks. Okay, so we're going to kind of go through these one by one. Let's start by thinking about the important sampled objective. So we want to go from something that is purely on policy, which only uses the latest data, to being able to use a little bit of past data. And we're going to start by looking at our original policy gradient objective, which is saying that this is our J theta, that's our gradient, right? And so to evaluate our gradient on the right, we always require samples from your latest policy P theta. You can't get samples from some P theta prime. You can't even get samples from your last iteration, right? Because they are an invalid approximation to your gradient, or invalid, whatever. Yeah, approximator to your gradient. Like this needs tau to come from P theta tau. Yeah. So this makes it fully on policy. It makes it like kind of a pain to approximate, right? So both the objective and the gradient require you to sample from your current policy, which means that anytime you take a gradient step, so you went from theta to theta prime, you need to resample. You need to resample everything. So pain. Okay. So the question is, can we be off policy? And so the main idea we're going to use is something called importance sampling, right? So what importance sampling is going to do is just going to say, if I have an expectation of it's more general than this. So before I instantiate this, if I have an expectation of a function, right, with respect to some distribution P, what importance sampling is saying is this is going to be equal to integral P of x, f of x dx, right? That's the definition of an expectation. What I want to do is I want to be able to evaluate this using samples from a different distribution Q, right? And so let's say I had samples from some distribution Q. How do I estimate this expectation using samples from a different distribution Q? Right? So that's what importance sampling is gonna do. How many of us know about importance sampling? How many? Few? Okay. So what importance sampling is going to do is going to say that let's take this objective, right? Which is the expectation under P. So it's saying that if you get samples from P and average F, it's going to give you the expectation under P. But I don't have samples from P, I have samples from Q. Okay. So what I'm going to do is going to do a simple trick. I'm just going to multiply and divide by Q, right? I'm going to say Q of X, multiply and divide by Q. Still going to have P, going to have F, dx, right? So all I did is took my expectation, multiplied it and divided by Q. That's it, right? Now we're going to do basically the same trick we did in policy gradient. We're just going to group these terms together, right? And so we can rewrite this thing now as expectation or integral of Q times P over Q times f of x dx, right? So now this is an expectation again, but the nice thing is the expectation with respect to Q, right? So you can write this as expectation Q of P over Q times F, right? So this and this are the same under a few conditions, but the point here is that why is this important? We started this expectation with samples from P. But now I'm allowing it to evaluate the same expectations under samples from Q. Right? So intuitively, you can think of it as like you get samples from Q, but you reweight each sample by like how likely by the ratio between P and Q. Okay? And so you can kind of think of it as like reweighting. They're just saying I'm gonna take samples under Q, reweight them by P over Q, and then take the expectation of the reweighted F. So what important sampling does is it allows me to evaluate an expectation under P using samples from Q. Okay, so why is this relevant to off-policy learning?
You have higher beta and higher beta.
That's right. So you can use samples from not just your latest policy, you can use samples from your previous policies if you import and sample it correctly. So what are the I make some assumptions here. Like this is not always valid. Like when is it not valid? Like when is this approximation invalid? So like where did I make a jump in logic? Right? So I multiplied it divided by Q. And then I rearranged these terms and I got the expectation. So like somewhere here, I made like an assumption. What is the assumption? Yeah. That's right. That's right. Yeah. So it's basically saying that Q of X cannot be 0 unless P of X is 0, right? And so it's saying that like for things, you need P and Q to have overlapping support. And support means points where the probability of both things is non-zero, right? So support over probability distribution is where its likelihood is non-zero. And you can't have Q be 0 where P is non-zero, right? Because this is going to go to infinity. And so basically this approximation is not valid. Or like my multiply and divide is not valid. If Q is 0 somewhere where P is non-zero, right? So whenever you do importance sampling, these need to have overlapping support, but that's usually like in a continuous space, it's not so bad. Okay, so you have to be a little bit careful there. Okay, so all we did is we said we're going to multiply and divide. We have our expected sum of rewards. We're going to multiply and divide by Q, right? We're going to now regroup these terms together and say this is going to be an expectation with respect to Q of P theta tau by Q tau times R tau, right? So we're just going to say it's expectation under a different distribution Q, but just reweighted by P theta tau by Q tau. Yeah. So this kind of gets us to be off policy as long as we know how to evaluate this thing. So we said our objective had to sample all the time. The nice part about this is we can keep this as the same all the time. It's just that this thing is going to change, right? So if you wanted to do updates, you could say, I'm gonna take that gradient step. That gradient thing can be approximated by some reweighted update. And I can keep the samples the same, but these weights will keep changing. Yeah. So that allows you to use some amount of past data. Okay. So there's some caveats here. We can try and rederive policy gradient originally from this perspective, and it's going to have some numerical challenges. So it's not a silver bullet to everything. It's just a nice framework that we can use to use prior data. Okay. Yeah.
Data buffer, you will keep feeding your past data.
Yes.
But the Q won't be reached. Let's say you update your
Q
will not be reached.
That's right. That's right. So you have to like change your estimate of Q over.
So, but you should be something like overlapping with the P, so you don't have another.
Because you don't have what of Q, sorry?
Have a.
You don't have control over the Q.
Overlapping with the P. It won't use this.
It doesn't have to be the same distribution. It just has to have overlapping support. So like, for instance, if you have a buffer and you have like, usually like the way you'd usually do this is that you clip these weights so that this thing never goes to 0. So like you approximate it by clipping the weights, but like if you want to be fully proper about it, then yeah, it may not work with a finite number of samples, but in practice, you can often just clip these weights from blowing up. So you're right that you don't have control over Q, but you do have control over Q in a sense because you're the one who drew the samples. But in practice, to satisfy the important sampling assumption, you can either clip the things or like collect enough samples that you have like reasonable coverage. Okay. So let's kind of like rederive policy gradient from this perspective of importance sampling. Okay. So what does importance sampling say? It says that our original objective, which is expectation with respect to p theta tau, can be rewritten as expectation with respect to q tau of p theta tau by q tau r tau. Yeah, we just multiplied and divided, rearranged some terms. What we're going to do is we're going to try and take the gradient of this objective, right? So we're going to start by taking the gradient of this objective. Now, the nice part about this objective is that this thing no longer depends on theta, right? So all of the pain we had with this thing depending on theta doesn't matter anymore. Only the inside thing depends on theta. Right? So if I take the gradient of this objective, I take the gradient with respect to theta, that gradient goes all the way inside. The expectation doesn't, it's more like supervised learning. Your expectation doesn't depend on theta. So the gradient is equal to the expectation under Q of the gradient of p theta tau by q tau r tau, right? All I did is take the gradient all the way inside. So we started from our original objective. We multiplied and divided by q. We rearranged the terms to get expectation q of p by q times r. Right? Then we took the gradient of this. We pushed the gradient all the way inside. And then we're going to say, let's set, we can choose q to be whatever we want, right? Let's set q to be data from our current iteration. Right? So our current iteration is theta I. Let's set q to be data from our current iteration. So what are we going to get? We're going to get expectation of tau coming from p theta I tau of the gradient p theta by p theta I tau r tau, right? So this is going to be our like the gradient of our importance sampling objective, right? And so all we did is we said we're going to take this objective, we're going to take the gradient goes all the way inside. And then we're going to set q tau to the data from the current iteration. And now the nice thing here is that if you look at this thingy, you can use the chain rule on it again, right? And it's basically equal to grad log p, right? So if I evaluate this gradient at theta equal to theta I, then this thingy becomes grad log p. And then we get back the same thing as policy gradient, right? So what does all of this mean, right? So like, let me repeat what we did. We did importance sampling, which says multiply and divide by q, expectation q of p over q times r. Then we said we're going to take the gradient. The expectation doesn't depend on q, push the gradient inside. If we set q to p theta I, which we can do, we can choose q to be whatever we want. And then we evaluate the gradient at the current theta I, then you get back exactly the same thing as policy gradient. Right? So the point here is that this objective, when we take the gradient of it and evaluate it at theta I, gives you the same thing as policy gradient. Right? So it's another way you can use to derive policy gradient. You can just write it as an importance sampling objective, evaluate it at your current policy. Okay, so I mean, this is not particularly interesting for us because we want to deal with off-policy stuff, right? But it's interesting because it like gives you the same thing as policy gradient. Yeah. Okay, I'm telling people are a bit lost. What?
I didn't get anything from you.
You can choose Q to be whatever you. Q is just you're saying that I can sample from some Q, and no matter what the Q is, I can get the I can evaluate an expectation under P by sampling from Q and then reweighting it by a ratio. Right? So I can this is a valid approximation to like my original objective, whatever I set my Q to be. Right? You just have to change the ratio. I'm saying that when I set Q equal to P theta I, and I evaluate my gradient at the current theta I, then you get exactly the same thing as policy gradient. So I'm saying that this importance sampled objective, when you evaluate it at the current time step, setting Q to the current data, gives you the same thing as policy gradient. Now you can do more with it, but you can at least derive policy gradient.
But in this case, you cannot do the cost data, which is like,
When you instantiate the approximation this way,
Yeah.
yes. So I'm just trying, we'll use it a different way, in the next slide. But the point here is that it's like a sanity check. As in, if I set theta equal to, if I set Q equal to P theta I, then it gives me policy gradient. So it's a sanity check. Okay. Does that make sense? It's a sanity check that this important sample thing isn't so crazy, right? It's just saying that I'm gonna replace J theta by this P over Q weighted expectation, and that's gonna be my important sampled objective. Okay, so what we really want to do is expand out P theta tau by Q tau, right? So when I look at this objective, right, what is it going to be? P theta is basically, as we remember from earlier, it's the product of the initial policy times, pi theta of A naught given S naught times the dynamics times so on, right? And Q is going to be, let's say Q was sampled under some policy. No. Sorry, guys. Okay. So let's say Q was sampled under some policy Q of AT given ST. The likelihood of a trajectory under Q is going to be P of S naught times Q of A naught given S naught times dynamics times Q of A1 given S1, etc. Right? So this is the trajectory distribution under pi theta. This is a trajectory distribution under, let's call it Q of AT given ST, right? So I'm saying that, hey, I'm going to do this important sampling thing. Important sampling is nice because I can sample things from some other distribution, some other policy. And P theta tau is going to be the product of the initial state times the policy times the dynamics times the initial state times the policy times the dynamics, right? And for Q, it's just going to be the same thing, but with pi theta replaced by Q, right? So if we remember how this, let me jog your guys' memory one sec. Let's go back to one of our previous lectures, right? Let's say we went to policy gradient. We go to policy gradient. If you remember how the policy gradient went, we derived this like likelihood step by step, right? So we said, here we go. Anyone see this? Yeah. So if you remember, this is like the likelihood of a trajectory, right? So we said this was the likelihood of our trajectory. This is the likelihood of our trajectory. It's the initial state times the dynamics times the policy. Initial state times the dynamics times the policy. Right? And all we're going to say is that in important sampling, we're going to have a P theta tau and we're going to have a Q tau, right? And we're going to try and take the ratio between them. And so Q tau is going to be P of S naught times the product of the dynamics. And what's going to change is the policy, right? The dynamics are the same. The environment is the same. The policy is going to be different. So the policy is going to be some Q of AT given ST, right? Which means that the ratio, what is the ratio between P theta tau and Q tau going to be? Just take those two things and just divide them. So what's the ratio going to be?
If you change the quality to, like, if it's Q and there's a different quality in the next one, wouldn't ST plus one change? Oh, wait, you're saying.
You're evaluating the likelihood of the same trajectory
Okay.
under both, right? So S's and A's are the same. It's just the Q and pi are different. Right? So it's like it's not like I'm sampling from pi and I'm sampling from Q. I'm always sampling from Q. But I'm just taking the ratio of the likelihood of the same trajectory under pi and under Q. Right? And so if I divide these two things, what do I get? Exactly. And you get a multiplication of pi over Q, right? So you get a multiplication from 0 to t of pi theta divided by Q of AT given ST. AT given ST. That's it. So you get a product. So remember, these are, if you remember a few lectures ago, I said never take the ratio of probabilities. It's bad times. And now we not only took the ratio, we multiplied it for t times. It's terrible idea. Right. So this is going to be bad for some reasons, which I'll talk about in a second, but does the ratio make sense? We took P and Q. The difference was the policy. The dynamics all cancel out. So it's going to be a product of the ratios between pi theta and Q. Pi theta by Q, pi theta by Q, pi theta by Q, multiplied over time. Sorry, I'm switching lectures today so much, but I think it's helpful. Okay, so let's see. There we go. So this was our objective, right? So we said we're going to take P over Q, and we're going to try and evaluate what P over Q is. And we said that, hey, P over Q, when you expand out the trajectory distribution, the dynamics all cancel out. You're just going to have a product of pi theta by Q, pi theta by Q, pi theta by Q, pi theta by Q, right? Over all time. So it's kind of like you take trajectories from one distribution and another distribution, and then you like weight the like policy likelihoods at every time step. Now this is bad because these are probabilities, right? And so these numbers can be pretty small, right? So like when you multiply a bunch of these numbers that can be pretty small, you quickly become numerically unstable. And so what you find in practice is when you look at importance weights, they either blow up or like go to zero. And so especially with any reasonable horizon, like let's say 200 steps, and you multiply the importance weights, like blows up to be unreasonable. And so the other thing that happens with it is that it's high variance, because when things are really small, any change in the value is a big deal, right? So the problem is that when these things are extremely small, like the variance of that estimator is super high. So it becomes like super sensitive to errors. And so the problem here with this important sample, I said it's not a silver bullet. Yes, you can sample from Q, but these things will blow up and become unstable. Yeah.
I have a question about motivation.
Mhm.
So is the point of using this important sampling so that we can use like samples from all of the past samples?
From at least some of the past samples.
Yeah, so does that mean what we're doing like with variation, we need to do this essentially also multiple times for different samples?
So you have to do the reweighting differently, but you don't have to retake the samples. So right now what we're doing in policy gradient is we're collecting a bunch of samples, right? Then we're updating the parameters, and then we have to collect samples again. And so you can take one gradient step, right? So what we're trying to do is at least allowing the update to take more than one gradient step. So we're saying that, okay, we're going to collect some samples, and then we're going to be able to take multiple gradient steps, and then we'll collect some samples again, and then multiple gradient steps. And so the point here is that because we can evaluate this objective under something that's not just the current policy, when I take multiple gradient steps, the theta will change, but the Q can remain the same. Right? And so that allows me, it's not going to be a silver bullet. We're still going to like only take a few gradient steps, but it's better than taking just one. Right? So the point is we did importance sampling. We did a sanity check that this is reasonable. But then we said, hey, this is numerically unstable. You multiply lots of probabilities, it's going to like blow up or blow down or whatever, go to zero, and it's going to be high variance. Yeah. So why are we doing all this? As we were just saying, we want to do it so that we can take multiple gradient steps. Right? We're not just taking one gradient step to recollect data. So what TRPO does is it does a little bit of an approximation. Like as you'll find out, most of our RL algorithms right now are just approximations to things that make sense. So we're going to start from our original objective, right? If you remember my first lecture, we said that we can rewrite, this is like this ancestral sampling technique where you sample things in sequence. You can also do this like stationary distribution technique where you just say, I'm going to sample states from the long-term visitation distribution of a policy, and then sample actions from my policy conditioned on my state, right? So it's saying if I run my policy for a long time, this is the likelihood I'll get to that state. This is the likelihood I'll take that action, right? So these two things are equivalent. Just going to be make our life a little easier. So these two things are equivalent. The problem here is that every time I need to evaluate this thing, I need to sample over and over and over, right? So important sampling was gonna help us deal with that. So important sampling, you can apply the same logic here. This thing is your Q. You can kind of think of this as your Q. This is your P. This is your Q, right? So it's the same logic of expectation Q, P over Q times F. Same logic that we applied in the last slide. Right? We're going to say that we're going to take this objective and we're going to apply important sampling to it. Right? So we're going to say this is going to be our Q, and we're going to reweight things by P theta S, pi theta by P theta I by pi theta. Right? So this is just going to be exactly the same thing we did in the previous slide. We multiplied and divided by Q, right? So we got a reweighted update. We're going to do exactly the same thing, but this is going to be our Q. Okay, so all we did is we rewrote, these two things are the same. We rewrote this Q update as P theta over Q, right? So all we did is we said, that was the original update. We're going to rewrite it in stationary distribution form. Stationary distribution form, we're going to write it by important sampling. Important sampling, this is going to be our Q. This is going to be expectation Q of P over Q times the sum of the rewards. Yeah. Now, what TRPO does is it does this approximation. So like, there's a typo here. But basically, this thing is easy to evaluate, right? Because it's saying pi theta I was your past policy, pi theta I is your new policy. So it's easy to evaluate. Now, this thing is hard to evaluate because it's like, this is like, what is the visitation of your state under theta? And what is your visitation of your state under theta I? So it's hard to compute those ratios, and they might be different, and they like blow up numerically. It's like the product of a bunch of time steps. And so that thing blows up. And so what TRPO does is it pretends that this thing is one. I'll explain why this, it's not that crazy. It's not that crazy, I promise. But it's going to pretend that this thing is one, and it's going to get this objective, which is much, much easier to deal with. So saying that this is basically saying take samples from your previous policy, right? And then this is an easy thing to evaluate, which is not a product of a bunch of stuff. And then you can take multiple gradient steps on this, right? So the nice thing is you can keep the same data and take multiple steps. Now, why is this reasonable? Yeah.
Is it because you're taking very small steps?
That's right. That's right. Basically, if P theta or if pi theta and pi theta I are close, right? So the difference between them is bounded. You can show that P theta and P theta I are also close, right? And basically, you can think of intuitively, you can say that if two policies are close, their long-term visitations are also reasonably close. Yeah.
Is there a typo on that?
There's a typo, yeah. This is a theta I. Yeah. Good catch. Yeah.
For the previous slide, right, where you have the ratios,
Mm-hmm.
if we still have that constraint, Q, the phi theta and Q being like not very fast and equal.
So there's no constraint there.
Oh, okay.
So this is saying for any Q, right? And so the problem with this thing is that it like blows up numerically.
But if I make the Q very close to phi theta, let's say here,
Mhm.
then I won't have that issue.
You still have like ratios that you multiply for 3 different time steps, right?
Okay.
And so yeah, it still tends to blow. So all that TRPO does is it constructs this is what they call a surrogate objective. So if you ever see surrogate objective in PPO or in TRPO, essentially what it's saying is that you sample states and actions from your past policy. And then you're going to approximate P theta by P theta I to be 1. And then you just reweight by pi theta by pi theta I. That's the diagonal. Jacob, could you note down this type? So basically, you're going to say that like all we did is we said if pi theta and pi theta are pretty close, then their long-term state visitations are not that far away. And they do a bunch of theory to show that this is reasonable. But the point is that we can get an objective which doesn't have this numerical blow up, and it can take multiple gradient steps. Right? And so this is that's the first step of TRPO. Right? Yeah.
Is this like why it's like called trust region? Is it like I trust the?
That's right.
the other-
So a trust region is basically it's like a ball around your current thing. It's like the regions you can trust. Yeah. But the first step of CRPO is constructing the surrogate objective. So the difference from our original objective was that we don't need to keep resampling. And we don't have this like multiplication of importance weights that is blowing up. So all that TRPO is doing in the first step is it's going from this objective we have to keep resampling to an objective we can evaluate on some fixed data. But theta and theta can't be that different. So when I'm saying I can't take infinite gradient steps on it, you can only take some gradient steps until that approximation is reasonable. But it's more than one. Okay. I think we're at time. But we'll do our seated discussions on Wednesday, and we will get back to policy again on next Monday. Thanks, folks. You survived.
That lecture for the process of it, because I was trying, look at the exact same thing, yeah. You know, we were trying to, you probably know, we were working the model and the policy.
Did you recommend?
And I kept trying to.
For probability. So this is a EE 126 class at Berkeley that I know about. It's like, it's called probability and random processes. That's the good one. Sorry, I didn't get a chance to post your video. It's a busy weekend, but I'll do it soon. Okay, sounds good. I'll post it. Yeah, like a probability class would be good. Most of the stuff I covered is probability and some linear algebra. But the linear algebra I kind of intuited. Most of it, the probability is tougher.
Sir, in the last time you talked about zooming up by Q1, but it's only valid if we assume multiple gradient steps instead of doing it on average. Like multiple gradient updates. Like first we are going to sample and then we then.
So I mean, you're gonna take.
So I wonder. I'm looking for something that can. Sample efficiency.
Do a gradient step, you're going to re-approximate the weights, and then you're going to do a gradient step.
Just need like 10 minutes.
No resampling. The tricky part is that, the important part is that you're not resampling, but you're recomputing the weights. Like, so what you're doing is a very basic set of samples.
Of course, it's like three. Not necessarily. So then they're like, stimulating T waves.
Yes. Yeah. So here's the tricky bit, right? Which I didn't really get to today, which is you're going to start from some theta I, okay? And initially theta and theta I are the same, okay? And then what you're going to do is I'm just going to keep moving theta to theta prime to theta prime prime, etc.
Like we just started the equation and we having some probability 0. Like initially it won't be. Like
I don't think we won't have probability 0
we
anyway.
will give some distribution when we are starting the equation.
Yeah, exactly.
I think you were saying like we will start with LQ or something.
Yeah, we can often start with that.
So okay.
So the point here is that at any iteration, okay, what's going to happen is you'll collect some data, then you'll set theta to theta I. Okay. Then what you'll do is you'll evaluate this objective, and then you'll keep taking steps to go from theta to theta prime. Okay, so you took one step. You went from theta to theta prime. So now what happens is you're not going to draw new samples, but this importance weight is going to change.
And how we are going to calculate p theta, like probability of
P theta or pi
pi
theta?
theta, sorry.
Because you know it's a Gaussian distribution or something, right? So you know that it's like you know that it's a policy, it's your own policy. Like if you remember our imitation learning lecture, we output the mean and variance of a Gaussian, right? So that gives you pi theta directly. So it gives you a number for pi theta.
But we are learning this theta right now. We don't know what theta is. Like
So theta I was your previous policy. and theta is your new is your thing you're updating. So saying that this was your previous policy. This is the thing that you're updating. You start these two as the same, okay? And then you keep updating theta from there. But every time you update the parameters, you can stick it back to your neural net. The neural net will give me a mean and a variance. The mean and a variance will give me a likelihood, right? And so I can evaluate this guy, I can evaluate this guy, I can get the ratio, right? And so the point is that pi theta is fully known to us.
Like what should I infer like in a meaning from this ratio? Like what this ratio?
It's telling you how different is the current policy from the past policy. So it's basically saying, okay, these were the steps, these were the.
It's like I just tell what my idea was, because last time when we were doing policy grading, like there was a problem like we couldn't trace because we were moving like very stochastic, like we were taking very big differences. We could end up like at not optimal. So that's why we are doing all these things.
No. So what we're doing is that, okay, so here's the issue. The issue is that you start with policy gradient, you compute the gradient, okay? If you start at theta, you're going to move to theta prime, okay? And now you're going to sample again. You took one gradient step, and then you got theta prime, you sampled again. And now from here, you're going to like take another gradient step with theta prime prime, you're going to sample again. So it's like the number of gradient steps to samples is like every time you take a gradient step, you have to like resample. So that's the problem, not an optimality variance problem. It's like or sampling problem. You have to keep resampling. So what I want to do is not have this process, but instead have a process that looks like take a bunch of samples and then go from theta to theta prime, theta prime prime, theta prime 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 before drawing another set of samples, right? So the difference is earlier we were doing theta to theta prime, we're drawing samples again. Theta prime to theta prime prime, you draw samples again. You're doing samples every time. And here what you're doing is you're not doing samples every time, you're doing samples every k times, right? But the problem is this objective, the original objective, I can't do that because it becomes an invalid approximation, right? And so what this importance, the way you can think of this importance sampling objective is I'm keeping the same samples, but I'm changing this ratio. Right, so I take one gradient step, I change the ratio. I take this gradient step, I change the ratio. I take one gradient step, I change the ratio. And this ratio, you can kind of think of it as how relevant are the previous samples to my current policy. Right, so it's like I took these samples, but now my theta has moved on to some theta prime prime. So like how relevant are these samples to what I care about at theta prime prime? That's kind of the intuition, right? So like it allows you to take these multiple gradient steps, but because we did this approximation, right? You can't do many gradient steps. Like these two, this approximation needs to be a valid one, which means that theta needs to be close to theta I. Right? So you can't take like infinite steps. You can take k steps before resampling. So it's better than before, but not perfect. Does that make sense?
Yeah, that's what I would say. Like a lot of people are.
Yes.
Is it on YouTube? Because I can't find it.
Let us see.
But yeah.
E126. This one?
Yeah, so can I access like videos or are you just
If you look at the
saying like the
term,
topic?
you're just running main dot with different arguments.
Oh, yeah.
So the whole point of the collab is you can change
Let's
the
see.
arguments in the collab and not. If that makes sense.
I think so, yeah.
Yeah, it has the learning materials here, lecture slides, supplementary notes.
I didn't even notice there.
Okay, so no like videos, right? Just like
I don't know if there are videos. Maybe they have. Yeah, I'm not sure.
Joko is.
Oh,
okay.
yeah. Maybe. Honestly, you can take